Hello and welcome back to the third part of video 5. We'll wrap up talking about the halogens, and then we will go through and try to figure out a way to remember which are going to be strong activators versus moderate versus weak, and same thing for the deactivators. So after watching this video, hopefully you can make it through all of these problems from your chapter 18 problem set. So let's go ahead and pick up where we left off in the last video. So we've looked at some examples of activating groups, and we looked at a deactivating group in the last video. That deactivating group was a meta-director. Now I'm going to talk about a different type of deactivating group, the halogens. These are special because they break the rule of deactivators. Because they are ortho-para directors. So we want to be able to explain why that's the case. So first of all, just some review. We went through already discussing how, from an inductive standpoint, halogens are going to withdraw electron density from the benzene ring, making it more electropositive. So it's going to be less nucleophilic. So that's why it's a deactivating group. Remember, the halogens were weird in that the inductive effect was very important. Now, if we look from a resonance standpoint, what do we see for the halogens? So let's go ahead and fill in our lone pairs here on our fluorine. And if I go ahead and from a resonance standpoint see what's going on, I'm going to go ahead and take a pair of electrons from the fluorine and bump it right here, and that means this carbon would have 5 bonds, so I'm going to have to push that there. So right away I see from my first resonance structure that I would expect to be pushing electron density into the ring. But it's a deactivating group, so that's why the resonance effect here, even though from a resonance standpoint, it looks like we're going to have negative charges in the ring, and that's usually activating. For the halogens, the inductive effect is more important than the resonance effect. Let's go ahead, though, and just finish this out, drawing the resonance. So if I start from the lone pair here and make it a bonding pair, I'm going to push these here. So I'm going to put the lone pair here with that minus charge. And now I still have this, I still have this, double bond. I still have 2 lone pairs here. And then if I move this pair of electrons here, I'm going to bump these up over here. And that formal, always checking to make sure that no formal charge here, net charge 0, net charge 0, net charge 0. Okay, let's draw one more. Let's see if I bump these here, bump this back up on top of here. Let's get a color I want. So now I have single bond, no charge on the fluorine, and no charge in the ring. Okay, so from a resonance effect standpoint, the halogens are electron donating, which means activating. So here we see these two effects in opposition to each other. Normally this wins out, but not for the halogens. So that's super important to know. So the induction effect is more important. So I'm going to say here that the inductive effect is going to be more important or have a greater effect than the resonance. And this is again, the halogens are the exception because normally resonance wins out. So now let's explain the regiochemical outcome we see when we have a halogen on a benzene ring, why the halogens are ortho-para directors. So let's investigate, again, the stability of the rhenium ions, those sigma complexes that lead to each of the regiochemical outcomes, the ortho, the meta, and the para. So let's go ahead and get started with that. So if I have attack at the ortho position, and just a reminder, we've got lone pairs here. Okay. So if I have attack at the ortho position, so what do we have going on here? There's a hydrogen here. I'm going to go ahead and just fill it in. I'm going to have a formal +1 charge here on this carbon. And I still have this and this, okay? And if you want to fill in those lone pairs, you can. All right, so in the ring now, let's go ahead and start moving electrons towards the carbocation. So I can't go from this direction because this carbon has 4 bonds on it. So I have to start over here. So when I do that, I have the double bond here. That means I have a formal +1 charge here in the ring. Okay, and then I can again move these electrons here. And when I do that, I'm going to have a formal +1 charge here. I'm going to have double bond and the double bond. Okay, and then can we draw any other resonance structures? So what if, since I have lone pairs, let me connect. I'm going to choose a different color here. So this, I don't know what to do, black maybe. So starting from this structure here, if instead of moving electrons around in the ring, if instead I took a lone pair from the fluorine and bumped it down, that's going to be this structure here. So I'm going to go ahead and take this lone pair, bump it down. The fluorine then is going to have a formal +1 charge, right? And then I still have 2 lone pairs on the fluorine. What's going on then in the ring? So here I still have this, and I still have this. There's still a hydrogen at each of these positions, by the way. If it makes you feel better to draw it in, go ahead. It's still there. So let's evaluate this. So here we have each atom has an octet, and yes, the fluorine has a +1 charge, but here this carbon has an incomplete octet, right? 6 electrons around it. Same thing here, same thing here. So here every atom has an octet. So remember, there's special stability associated with that. So I'm going to pay attention to that, because remember, we're trying to figure out why it is that halogens are ortho-para directors. So we know then that the intermediate that brings us to the ortho product and the intermediate that brings us to the para product must be stabilized somehow relative to that of meta. So now let's go ahead and take a look at the meta intermediate, the uranium ion or the sigma complex. So if I have attack at the meta position here, so I'm going to take this pi bond, use it to attack here. Nitro group is there, so then my plus charge is here. And I still have these bonds in the ring. Okay. And so now I'm going to take a pi bond and move it towards the carbocation that's in the ring there. So when I do that, then my formal charge moves here. I still have 2 pi bonds in the ring. And then I can do that again. This time I'm going to move this pair of electrons here. And now I have, oops, red, this, right? And so notice with the meta attack, I never get the positive charge here, right? At this position. Okay, so it looks like a secondary carbon with the plus charge on it for each of these. And so it's an incomplete octet, incomplete octet, incomplete octet. So again, the transition state that leads to this intermediate is going to be higher in energy, destabilized relative to this one. Okay, now let's look at the para. So if we have para attack, so using this pair of electrons here, attacking, nitro group adding here, that means that the plus charge is here. And yes, there's a hydrogen here, 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 if you want to draw that in. Okay, so we still have this and this. Okay, so let's go ahead and start pushing electrons around. So if I move this here, now I have a formal plus charge right here. Okay, and I still have this. Okay. So notice here, this is just like this here. Okay, let's keep going. So I can move this here. And when I do that, I have my plus charge here, and this, and this. And taking this structure here, if instead of moving the electrons in the ring, if instead I had taken a pair and bumped it down here, I'd have the fluorine with the plus charge. And then notice every atom would still have an octet. So this is especially stable. So when you find, as part of the resonance hybrid, something that's especially stable, we know that the transition state leading to that intermediate is stabilized. Okay, so a lower energy of activation to get there. Whereas if we had found something that was especially destabilized, that would raise the energy of the transition state leading to it. So here we can rationalize why halogens are ortho-para directors instead of being a meta-director. Okay, so what we're going to do now is we're going to take a look at the handout. And again, this comes from your textbook, this table. 19.1, you'll notice that in addition to separating, so up here we have the activators, and down here we have the deactivators. So you can practice testing yourself. You can make little flashcards that put examples of activators, and then these are examples of deactivators. Now what we want to go into explaining is how to remember which activators are strong versus moderate versus weak, and which deactivators are weak versus moderate versus strong. So I'm going to start from one end of the spectrum, the strong activators, and work my way down. So let's go ahead and get started with that. So this is what we're trying to do now. So we're going to start with the activators. I'm going to start with the most extreme, so with the strong activators. So the strong activators have, all of them except for one, are going to have a lone pair, LP, that's adjacent, so next door to the benzene ring. And that lone pair can be delocalized into the ring. So phenol, for example, with that OH group, has a lone pair that can be delocalized into the ring. Another example would be anilines, amino group, okay, has a lone pair next door to the benzene ring that can be delocalized into the ring. Okay, so that's how you're going to remember who the strong activators are. So notice here you've got a lone pair, 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 and for all of these you can delocalize them into the ring. Okay, and I'm just going to point out, since I'm showing this here, when you have an OR group, you expect it to be strong based on what I just told you, but it turns out it's moderate, so that's kind of a weirdo. All right, let's go and take a look next at the moderate activators. So moderate activators also have a lone pair adjacent to the ring, but it can be delocalized outside the ring or away from the ring. So for example, if you have an amide where the nitrogen is the part that's directly bonded to the ring. This lone pair, so this is I'm just going to draw in here, you've got a nitrogen carbon bond here. I can bump this down here, and then you can bump this up, right? So the lone pair can be delocalized outside of the ring. And here, let me just put in our group here, same idea. I can take a pair of electrons, bump it down here, and then push this up outside of the ring, okay? And here is your alkoxy group here that you would expect to be strong, but it is moderate, and that's just one of the weirdos you have to know about, okay? So this one is a little strange and doesn't quite follow that rule. So a trick to help you remember the strong and the moderate activators is this O- or /P, because this slash, if I just kind of tip it a little bit, it looks like OLP. And so you can come up with the little mnemonic, one lone pair on an atom directly bonded to the ring. That's what you see in common with the strong and moderate activators, right? So what about the weak activators? So the only example of a weak activator are the alkyl groups. So R is an alkyl group, okay? So alkyl groups are weak activators. Remember, these, for alkyl groups, you just have the induction effect. There's no resonance effect. And remember that the more R groups there are, the more polarizable, the stronger that inductive effect is going to be. So now let's check out the deactivators. We're going to start with the weak deactivators first. And so those are going to be the halogens. So with the halogens, we just talked about those earlier. Those are ortho-para-directors, and that's unusual for deactivators because the other deactivators are meta-directors. So remember, for the halogens, the inductive effect is more important or outweighs the resonance effect. Okay, who are the moderate deactivators? So if I look at this table here, I see the moderate deactivators here. So these have a pi bond to a more electronegative atom. So something like a benzaldehyde, for example, where you have a carbonyl carbon that's double bonded to an oxygen, which is more electronegative than carbon. So they're going to withdraw electron density from the ring via resonance. And the little trick for remembering these guys, the meta-directing deactivators, so M for meta, M for multiple bond. So a double bond is an example of a multiple bond, right? A multiple bond to a more electronegative atom. So again, the M's. M for meta, multiple bond to more electronegative atom. So let's look at an example of that. So here's benzaldehyde. Okay. So directly bonded to the benzene ring is this carbon that has a pi bond. So a double bond is an example of a multiple bond to a more electronegative atom. So I should be able to show how we can withdraw electron density from the ring via resonance. So let's go ahead and draw resonance for this. So if I take this pair of electrons here, push it there, and then I can bump this up here so that I have that. Let me get the blue here. And now this has a formal minus charge on it. And now I've added double bond there. So now this has a formal +1 charge. Remember, there was no net charge here, so make sure your formal charges add up to 0. And let's fill in what else we're missing. Okay, and then I can move electrons around in the ring. So now the formal charge is here. And like so. Let's do this again. So now I have a plus charge there. There's my plus charge. Okay, and then if I, let's see, oh, I'm missing this. I was like, why is there only, there we go. And now if I take this back down, boom, boom. Okay, no charge. Good. So notice here, we see plus charges in the ring. So we are withdrawing electron density from the ring thanks to this group here. So the aldehyde here is serving as a deactivator. Okay. All right, so what about strong deactivators? So the strong deactivators, we've already talked about nitro groups. Nitro groups deactivate both their electron withdrawing by induction as well as by resonance, right? And here, if you have a quaternary ammonium ion, or if you have a carbon that's bonded to halogens, so for example, with our C, let's just do this one here. Carbon with, let's do fluorine. So each of these bonds is really polarized, so that carbon has a partial positive charge on it. So it's going to pull electron density, withdraw electron density from the ring. So for both of these deactivating groups, they're strong deactivators because of the powerful induction effects. When you have that, this has a formal +1 charge on that nitrogen, it's going to suck electron density through a sigma bond from the ring. So that's why it's induction. So what we're going to do in the next video is we're going to now put all of this information together and predict the product or products that we expect to form. So here, for example, we have phenol, and so we have the OH group. This is a strong activator. And that OH group is an ortho-para director. So if I'm adding group Y to the benzene ring, what do I expect? I expect to get both the ortho and the para product. There's our para. Now, you might think that or the ortho product, that we should have more of that relative to the para, and I know that I showed you an example where that was the case, and I say that that would be, you know, I would not be surprised for you to guess that, since there are two ortho positions, right, versus just one para. But most of the time, this group here, the bigger it gets, the less likely the ortho attack is going to be possible due to steric hindrance. So you're going to notice that I'm going to go ahead and, just to make your life easier, I'm going to tell you that para is usually the major product. So when you do these problems, give me the para product as the major product. So give para as major product. Okay. All right, so we'll pick up in the next video with real examples to practice on. Stay tuned. That'll be video number 6 for chapter 18.